Hello everybody and welcome to the difference of squares. This theorem tells us that if we have a quadratic equation, which is the difference of two squares, then it can be written as the product of two binomials, where the first binomial is the sum of the square roots and the second binomial is the difference of the square roots. We'll just quickly show that this is true by multiplying out a plus b times by a minus b. So we have a times a, which is a squared. Then we have a times minus b, so we'll get minus ab. Then we'll have b times a, which is plus ab. Then we'll have b times minus b, which is minus b squared. Now, as you can see, the minus ab and the plus ab will cancel each other out, so we're left with a squared minus b squared. So if we have a quadratic, x squared minus 25, we need to look at what we've squared to get x squared. We've squared x. And what have we squared to get 25? We've squared 5. So the expression can be written as x plus 5 times by x minus 5. And likewise, y squared minus 16 would give us y plus 4 times by y minus 4. Now, to use the difference of squares, there are a few criteria you have to meet. So firstly, there must only be two terms. So if we had, for instance, x squared minus 11x plus 18, you cannot use difference of squares on that. There are three terms. Next, there has to be a minus sign in between the two terms because this only works for the difference of squares. It doesn't work for the sum of squares. So if we had x squared plus 25, we can't use this theorem because x squared plus 25 is the sum of two squares. Also, the coefficients must be perfect squares. So the theorem doesn't work on x squared minus 15 because 15 is not a perfect square, and it also doesn't work on 2x squared minus 25 because although 25 is a perfect square, 2x squared is not a perfect square. And finally, the degree has to be even or 0. So x squared, x to the power 4, x to the power 6 is fine, and anything to the power 0 is 1, so that's also okay. But if we had x cubed minus 16, we could not use the difference of squares on that either. So now we'll just run through a few examples. So if we have t squared minus 36, we would have to square t to get t squared, and we would have to square 6 to get 36, so we can factor this as t plus 6 times by t minus 6. And for 81 minus b squared, well, 9 squared is 81, so we have 9 plus b times by 9 minus b. And for 64 minus w squared, we have 8 plus w times by 8 minus w. Now in D we have 36y squared minus 16. And we know the square root of 16 is 4, but we also need to take the square root of 36y squared, which is going to be 6y. So this can be factored as 6y plus 4 times by 6y minus 4. And factorising 9w squared minus 64 gives us 3w plus 8 times by 3w minus 8. And we can factorise the expression in f as 5v plus 6 times by 5v minus 6. In G we have 3z plus 2 times by 3z minus 2. And in H we have 5c plus 7 times by 5c minus 7. Now if we have 9m squared minus 100, that factorises to 3m plus 10 times by 3m minus 10. But what happens if we have 25w squared minus 150? Well, you can see 25 is a perfect square, but 150 isn't. So what do we do next? Well, we have to look for a common factor that when taken out leaves us with two perfect squares. Now, a bit of a clue here is you can see that 150 is divisible by 25. And if we did take 25 out, we're left with w squared minus 9 inside the bracket. And we can use the difference of squares on that. So our final answer would be 25 times by w plus 3 times by w minus 3. In K, you find that if you take a factor of 9 outside the brackets, you're left with 9y squared minus 25, and that can be factored using the difference of squares. So your final answer is 9 times by 3y plus 5 times by 3y minus 5. And for the last expression, we can take a factor of 6 outside the brackets, giving us 9a squared minus 36. This can be factored using the difference of squares, giving us the final answer of 6 times by 3a plus 6 times by 3a minus 6. Well, that's it for this video. As always, thanks ever so much for watching. If you could hit the like and subscribe, that'll be fantastic, and I really hope to see you soon.